Hello everybody, this is Mr. Bowman. So today we are going to be looking at 8.2, how to do those difference between means, the double hypothesis test, if you will, when we have small samples. So we already looked at how to approach them when their samples are 30 or larger. They get those large samples. So today we're going to see how they differ just a little bit, and how to use your calculators to make sure that you get everything sorted out. So anytime your sample size is less than 30, you do want to make sure they are randomly selected. This is the same as the large sample sizes. Okay? They still need to be independent. Everything up to this point is exactly the same as when we looked at before. And now, since it's less than 30, we do need the entire population to have a normal distribution. Okay? If that is not the case, if you have a skewed distribution or uniform distribution, this is not going to work. So you want to make sure that has a normal distribution. Okay. Something else on your calculator that you're going to run into is they're going to ask if you want it pooled. Pooled estimate for the standard pooled estimate for the standard deviation. So what that means is you want to know if the population variances are equal or not. Generally, just select not pooled on your calculator. Okay. So run as not pooled. Okay. Just ease it up, run it that way every time, you'll be fine. Okay. All right. So jumping into the actual tests here, the first one isn't going to change. You're going to use the same HO, find the level of significance, use a little mark to establish which one your claim is so you don't forget. That's the same. Likewise, step 3 is going to be the same. So it's, once again, just step 2 that's changing up a little bit. So you're going to find the critical value. That's using that table B on the back of your formula sheets there. You're going to find a degree of freedom, and then you use the 2-sample test, but now it's going to be the 2-sample t-test to find your test statistic. Okay, it's the same kind of crazy formula from yesterday to find your test statistic, with one small exception. So I'll write it out for you, but I'm assuming most people are going to go to the 2-sample t-test. Before we get too far along here, I didn't write anything in degree of freedom, you might notice, and that's because whenever we do that, it's 1 minus your sample size, but we have 2 sample sizes. So whenever you do this, you're going to use the smaller sample size to get your degree of freedom. So it's n minus 1, make sure you use your smaller sample size. Now, the formula for this thing, as promised, is a little bit chaotic. So t equals, because it's a t-test, x bar 1 minus x bar 2 minus mu 1 minus mu 2 over, all of that's the same. Big difference here is, remember, you're using the sample standard deviation, so S, as opposed to the population standard deviation, which is sigma. So there you go. So that's how we tackle those. So there's the formula if you want to use it. I'm assuming most people are going to go to the 2-sample t-test, and that's perfectly fine. All right. Now, if you remember yesterday in class, I did say it was kind of a weird pattern. Well, they got it better this time around. I don't know why, but so we're going to do all of the sample 1 parts first. And then we'll hit all of the stuff from sample 2 second. Okay. And then on the bottom, you are going to select, as always, what kind of test we're using by using the mark for our alternative. And now the new one, it's going to pick pooled, yes or no, and you want to pick no. Okay, just make, as I mentioned earlier, just leave that as not pooled, and it'll make it easier because it will be one less thing to worry about. Okay. All right, so just labeling these. mean from sample 1, standard deviation from sample 1, and the sample size from number 1. Mean from 2, standard deviation from 2, and the sample size from sample 2. Okay. So these are nice because it is broken up, all the stuff from sample 1, all the stuff from sample 2, but I don't know why they didn't do that the first time, but that's all right. All right, getting to quick examples here to make sure that we are getting this sorted out. I like to label my stuff at the beginning as we get far along here so I can remember which one's 1 and 2. If you want to call it F and M for Firestone and Michelin as opposed to 1 and 2, that's fine. It's not a big deal. So we have consumer reports testing the stopping distance in feet of 10 Firestone tires and 12 Michelin tires when traveling on ice at 15 miles per hour. The results are shown below. Can you conclude that there is a difference in the mean stopping distances of the two types of tires using a significance level of 0.01? Assume the populations are normally distributed and the population variances are not equal. Okay, so that population variances is about the pooled and not pooled. Remember, you can just say it's not pooled all the time and you're good, but this one you have to say it's not because it's not equal, so you wouldn't have a choice there. Okay, getting this one going here, we need to find our hypotheses. So in this one, our conclude that the difference in the mean stopping distances are not. So, sorry, I'm not moving around enough. My light's turning off. Okay, so we want to know, is there a difference or not? So we're going to say, is mean 1 equal to mean 2 or not? Okay, and looking back here, can you conclude that there is a difference? So that means our claim is that there is a difference, so they are not equal. Okay. It's a two-tailed test. And ready to move on. So jumping in here, getting most of our stuff from our calculator here, and that's perfectly fine. But so first up, our critical value. We need our degree of freedom. So I'm looking at my smaller one here. So we had 10 and we got 12. So our smaller one is 10. So that means my degree of freedom is 9, one less than that. And then this is a two-tailed test. So I want half of alpha, which is 0.005, cutting that 0.01 in half. And then using our table there, looking up, it should be 3.25. So then that is going to be our rejection lines there. So that is two-tailed, so it's plus or minus. So I get negative 3.25 and positive 3.25, shading on the outsides. And then in your calculator, doing your two-sample t-test, you will find out that your test statistic is negative 1.50, which is right about there, which is outside of our shaded region. So we are going to accept our null because it's outside the shaded region. So accept that means we're rejecting this one. So we are rejecting the claim. And therefore saying that their tires are more or less equivalent. So there is not much of a difference, statistically speaking. All right, number 2. Manufacturer claims that the watt usage of its 16-inch or 17-inch flat panel monitors is less than that of its leading competitors. So try to be better. You perform a study and obtain the results below at a significance level of 0.1. Is there enough evidence to support the manufacturer's claim? Assume the populations are normally distributed and the population variances are equal. So, key here, normally distributed. Still setting that to not pooled, even though it says they're equal, just to make it one less thing I have to worry about. All right, jumping in here, HO, HA. They're claiming that it is less than their competitors, so that'll be down here, too. makes this one greater than or equal to. Claim there. Less than makes it a left tail test. We got that taken care of. Calculating some stuff here. Yeah, okay, so we did a rejection regions for this one. Let's do a P versus alpha for this one just to mix it up and see both of them. So doing our test here, we don't need a critical number, right? Because we don't need those lines for the rejection region. So I just need to find my P, which you get from your 2-sample t-test, and find out that it is 0.1813 if you do that correctly. Going into P versus alpha. So 0.1813, my alpha is 0.1, so that makes this greater than step 3, interpreting there. If that's greater, that means I'm going to accept my null and reject my claim. So in this case, is there enough evidence to support the manufacturer's claim? No. No, there's not. So there's not statistically different. And there you have it. See you later.